Okay, we're talking about chemical equilibrium today. So the first thing that you need to be able to distinguish is the difference between an open system, a closed system, and an isolated system. So an open system, you'll see in your textbook, they use a picture of an open pot that doesn't have a lid on, that's on a stove. So that represents an open system where the matter as well as the heat or the energy inside the pot is free to interact with the environment. A closed system is, for example, like a pot that has a lid on, but it can still receive heat from the stove top. So energy can be exchanged, but the matter that is inside the pot stays inside it. Okay, and then an isolated system is like what's supposed to be a flask that keeps your coffee hot. The idea is that no matter can be exchanged with the environment. So what's inside the flask stays inside, and heat, energy can also not be transferred between the two. Right. Then dynamic equilibrium. Equilibrium means that in certain reactions, if you have A and B that reacts to form C and D, that reaction can only go in one direction. But other reactions are what we call reversible reactions. So that reaction can take place in the opposite direction as well. So A plus B can form C plus D. But C plus D can also, again, form A plus B. So, in a reversible reaction like this, we can get to a condition that we call equilibrium. Now, equilibrium, you have to know the definition of dynamic equilibrium. It's not just equilibrium, it's dynamic equilibrium. This means that the rate of the forward reaction equals the rate of the reverse reaction. So this reaction that forms C and D happens at exactly the same rate. They are equally fast than the reverse reaction where A and B is formed again. So this is not static, so that A and B has now formed C and D, and now everything just stays as it is. It's dynamic. A and B is constantly forming C and D. C and D is constantly forming A and B. Now, there's conditions for dynamic equilibrium to take place, and that those conditions, the conditions, the equilibrium conditions, are that to get a dynamic equilibrium, you have to have an isolated system, and the equilibrium conditions need to be constant. Now, the equilibrium conditions are temperature, concentration, and pressure. Okay, so those three things, temperature, concentration, and pressure, needs to stay constant. And while they stay constant, we can have equilibrium in an isolated system. Okay, now, yeah, A and B form C and D at exactly the same rate that C and D forms A and B again. If we write the arrows like this, this means that the forward reaction has a faster rate than the reverse reaction. So this means that A and B is forming C and D much faster than C and D is forming A and B again. So This indicates the difference in the rate of the reaction. So if we have a faster rate of the forward reaction, then we say that the forward reaction is biased. Okay, so the forward reaction is biased if the rate of the forward reaction is faster. In this example here, the rate of the reverse reaction is faster than the forward reaction, which means C and D is forming A and B faster than A and B is forming C and D. So the rate of the reverse reaction is faster, so then we say the reverse reaction is biased. Right. Now, these equilibrium conditions we can draw a graph like this for equilibrium. Okay, so what happens here is A and B reacts to form C and D. I chose just any random balancing numbers to just show you what I'm trying to say. So according to the balancing numbers, 2 moles of A is reacting with 1 mole of B to form 4 moles of C plus 3 moles of D. Okay. Now, in this graph, what is indicated is that initially, before this reaction starts, we only have A and B in this container, right? C and D hasn't formed yet. So there's 0 C and D. And maximum, A and B. Now, as A and B start reacting to form C and D, because this is a reversible reaction, C and D start reacting to form A and B as well. So A and B initially, they are decreasing because they are forming C and D. And C and D, as they are formed, their concentration increases, right? But now at a certain point, the rate at which C and D forms A and B becomes equal to the rate at which A and B forms C and D. And because this makes this as fast as this makes this again, now their concentrations are all going to stay constant. The reactions are taking place the whole time, but their concentrations now remain constant. And the moment this happens on the time axis here, that time that they start having constant concentrations, that we call the point of first equilibrium. So now equilibrium has formed. So you recognize equilibrium when concentrations of all the reactants and products stay constant. Right. So that's how we draw the graphs here. And remember that the products will always have 0 concentration initially. Okay. Now, the next thing we can do with this is we can do calculations in which we calculate what is called the equilibrium constant. Equilibrium constant, Kc. Now, in acids and bases, we also calculated a equilibrium constant. So this is not a new concept. So the equilibrium constant basically just tells us whether this reaction we have, the forward reaction, whether this is really productive. If we have a relatively high equilibrium constant, higher than 1, then it means that more products are formed than reactants. And if this was an industrial process, then it would be economically feasible for us to actually go for this reaction. But if the Kc value, the equilibrium constant at a certain temperature for a certain equilibrium reaction is 1 or smaller than 1, that would mean that we have, while we're letting this reaction take place, the products are forming reactants again so fast that we really are not getting an economically feasible product. So then we would want to change the equilibrium conditions so that we have a higher, so that we can have a higher yield. Okay. So that's why we do this calculation, is so that we can just know if we are chemical engineers working for a company, so that we'll be able to tell them, yes, this reaction will work under these conditions, or no, it won't. We have to change the conditions. Okay, so we calculate Kc with this general formula. When you write exam or test, you never write down this general formula. This is just a guide for you to know what you need to do with a specific reaction. So this, what I've written in green here, you never write down on a paper. This just stays in your brain. Okay? So it's the products multiplied by each other, the concentration. It has to be the concentration. If they didn't give you concentration here on this axis, let's say they gave you moles, then you have to use this formula that concentration is moles divided by volume and get the concentration of each mole of substance first before you can put it into this equation. Okay, so these has to be concentrations. So the concentration of the products multiplied by each other, and that concentration of each product you multiply, you raise to the power of its balancing number. So product 1 to the power of its balancing number multiplied by concentration of product 2 to the power of its balancing number, divided by the concentration of the reactant to the power of its balancing number multiplied by reactant 2 to the power of its balancing number, right? And what's also important here is that you only, when you substitute, you only use substances, and this is important, you need to remember this, that you only use gases and aqueous solutions. Only reactants and products that are in one of these two phases, only them you substitute into this formula. Anything that's a solid or a liquid, you do not substitute. Its value is just 1. Okay, so you don't use it in your, you don't even put it in your formula like this. You only put those that are in gas phase or aqueous phase. Okay. So now in this specific example, this would mean that this Kc value is C to the power of 4, the concentration of C to the power of 4, multiplied by the concentration of D to the power of 3, divided by the concentration of A squared multiplied by the concentration of B. And that one doesn't have a balancing number, so that's just to the power of 1, which we don't write. Now, when we substitute the actual values, if they gave us a graph or a table or whatever with concentration on this axis, then we can directly just substitute. If they gave us moles, then we need to first use this equation to calculate the concentrations so that we can substitute the concentrations in here. Then we get an answer. I didn't calculate this answer, but you get an answer that doesn't have a unit because all of these units are exactly the same. They cancel out. So a Kc value has no unit. All right. So it doesn't have to be in a graph. They could just give you values. They could just tell you A has a concentration of 7 moles per cubic decimeters, B at 3, D at 1, and C 0.5. And then you just calculate from the values given. All right, so please do summarize this in your book and then do exercise 15 before you go on with this video. Okay, now the next part of the calculations that we need to be able to do is to calculate equilibrium concentrations if they are not given. Okay, so in the previous examples, in all of those, you had been given each one of those reactants and products concentrations or moles so that you could determine the concentrations so that you could eventually calculate the equilibrium constant. But they could just give you a balanced reaction and tell you how much you had of one thing in the beginning and how much you had of another thing after reaction. So what you do then, and you will definitely get a question like this in the exam, you can be sure of that. So there's a general pattern. All you do is you study, you memorize what you need to put in this table. And then no matter what they ask you, you draw this table, you write down these things that you've memorized, and then you just do what you've written here. Okay. So you always follow the exact same little pattern. So let's say this is the balanced equation they gave us. 2a plus b forms 4c plus 3d, and that's a reversible reaction that eventually reaches equilibrium. Okay, now initially given in this example is that we had 2 moles of A that we reacted to 3 moles with 3 moles of B. And when we eventually got to equilibrium, we had 8 moles of C. Right. So now that's what's been given, and now they're asking us, okay, so please calculate the Kc value. Right, so now in order to calculate the Kc value, let's see what we need. Kc, in this case, is going to be D, the concentration of D at equilibrium, to the power of 3, right? Multiplied by the concentration of C to the power of 4, divided by the concentration of B to the power of 1, which we don't write, multiplied by the concentration of A squared, right? That's what we need. So now we don't have any of that. because we don't have even one concentration at equilibrium. So in order to calculate the concentration at equilibrium, we write this grid. A column for each reactant or product, and then, or a row. No, these are columns. A column for each reactant or product, and then a column for your memorized little pattern. Then the first thing you have is you balance. Then you need to write down the initial mole or concentration that you have before the reaction happens. Then what has been used, so the reactants would be used, or what is formed. So the products are formed most now. So used or formed. How much you have at equilibrium, and then concentration is mole over volume. So this formula you're going to use if what was given here was moles. If they gave you concentration, then you don't have to convert to concentration. But what's important is that if they gave you moles, you're going to need the volume. So they need to tell you, you need to read in the question what the volume of this container is. Okay, so in our case, let's make it 2 cubic decimeters. All right, so that information you need to find in the question. So now, because these are products, we know that initially, before the reaction starts, we have 0 mole of this. Right? Everything is in mole here. Now, what they also told us is that C, at equilibrium, we have 8 moles. So we fill that in as well. C at equilibrium, we have 8 moles. Okay. Now, the used or formed. We write this in terms of X, and that X we get from the balancing numbers. So from these balancing numbers, we know that 2 moles of A will react with 1 mole of B to form 4 moles of C and 3 moles of D. Okay? So for every 2 moles of A used, 1 mole of B is used, 4 mole of C is formed, and 3 mole of D is formed, right? So this means in terms of X, we use, so decrease, 2X. Yeah, we use, decrease, X. Yeah, this is a product, so we're going to form, increase, 4X. This is a product, so we're going to form 3X. Okay. After you've written this in terms of X, now you look for a whole column where you have all 3 of these. You have initial, used or formed, and at equilibrium. So we have only 2 there, only 2 there, only 2 there, but we have 3 there. So now what you do with this, where you have 3, is you make a mathematical formula or an expression with that. So that means we have 0 mole. We add 4x mole. And then we get 8 mole. So 0 plus 4x is 8. And now we solve for x. So after you've written these, you look for a column that has 3 pieces of information. You use that as a mathematical expression to solve for x. So x is 8/4, which is 2 moles. Now you know what x is. And now you solve for x, and then you substitute the x everywhere. So x is now 2. So this means minus 2 times 2, which means minus 4 mole. Yeah, it's 1x, so it's minus 2 mole. Yeah, this is plus 4x, and x is 2, so it's plus 4 times 2. So it's plus 8 mole. Over here, it's plus 3 times 2, so it's plus 6 mole, right? Plus 6 mole, plus 8 mole, minus 2 mole, minus 4 mole. And now we can see here, we had 6 mole of A, we used 4 mole. How much would we have left then? 6 minus 4 gives us 2 mole at equilibrium. We had 3 mole, we used 2 mole of B, so we're left with 1 mole of B. We know already we have 8 mole of C, and for D, we had 0, we formed 6, so we have 6 mole of D at equilibrium. Now we still need to calculate Kc. For Kc, we need concentrations. We have moles. So now we need to use C is equal to N over V to get from mole to concentration. And we know our volume for this example is 2 mole. So all of them are in the same 2 cubic decimeter container. So we divide all of them by 2. So yeah, the concentration is 2 over 2, which gives us 1 mole per cubic decimeters. Yeah, the concentration is 1 over 2, which gives us 0.5 mole per cubic decimeters. Yeah, the concentration is 8 over 2, 4 moles per cubic decimeters. Yeah, the concentration is 6 over 2, which is 3 moles per cubic decimeters. Okay. So this is what you need to understand before we go to Kc. Just once again, this you memorize and you write it down immediately. So you balance first if it's not given as a balanced equation. You write down the moles or the concentrations. Initially, everything that they give you, used or formed, the products will be used, the reactants will be used, so that would be minus, and the reactants would form, so that would be plus, and you write all of that in terms of x, and you get the amount, how many x's from the balancing numbers. Then you look for one of these where you have 3 pieces of information, and you use that to solve x, and in all of the used or formed blocks, you now substitute the x. That would give you enough information to get the moles at equilibrium. And from moles at equilibrium, you need to go to concentration. If they had given you concentration, then you don't have to do this. But I haven't seen many examples in exam questions where they actually give you concentrations. In most of them, they give you moles, and you need to convert in this last row. Okay. Now, from there, we can go to the Kc value. So the Kc value in this case we already wrote down. That's how we would get it. So now we just substitute everything we got here. So D is going to be 3 to the power of 3. C is going to be 4 to the power of 4. A is going to be 1 squared. And B is going to be 0.5. Okay. And then you get an answer, and that answer has no unit. Okay. So now, please use this as an example. There are also more examples in your textbook. They can give you this in any order, where they give you this and they ask you that, for example, or they give you the Kc and you need to work from the Kc to their upward. As long as you understand how this works, you can do any calculation, left or right, up or down, in any way. All right. So use this and do exercise 16 in your textbook, please, before you go on with the rest of this video. So the next concept we need to do is Le Chatelier's principle. Okay, now Le Chatelier's principle states that if the equilibrium in a closed system is disturbed, how you disturb that is you change one of the equilibrium conditions. So you change the pressure, you change the temperature, you change the concentration. So if that equilibrium is disturbed by doing that, then the system will react. How will it react? It will work against the change and eventually form a new equilibrium. Okay. So what that means, that if you change the pressure by increasing the pressure, the system will decrease the pressure. If you increase the volume, okay, if you're going to be able to increase the volume or decrease the volume. But now you need to remember that the system is just a lot of chemicals. It can't do anything to the volume of the container. But C is equal to N over V. So what it can do to work against, what's actually the problem for the system is that if you increase the volume, because volume and concentration is inversely proportional, you are decreasing some concentration. So what the system will do is it will work against that decrease in concentration by increasing the concentration again. Okay. What the system will do if you increase pressure, remember in the particle model of matter, particles that collide against each other cause pressure. So if you have more particles in a certain volume container, you're going to have high pressure. If you have the same volume but less particles, you're going to have lower pressure. So what the system will do to lower the pressure is it will decrease the concentration. Okay? So the system decreases pressure by lowering concentration. If you have an increase in volume, the problem for the system is that you had decreased the concentration. And what it will then do to get back to the same concentration, is it will increase the concentration. Okay? I'm going to show you what it does to increase the concentration now. If the change that happened in an equilibrium system was that concentration of something increased, let's say concentration of A increased, the system will decrease the concentration of A. Okay. Now let me just quickly talk about, before I talk to you about temperature, let's talk about chemistry first. So eventually you see pressure, volume, concentration changes. The system will try to decrease pressure by lowering concentration. It will work against an increase in volume by increasing concentration as well. It will work against a decrease in volume by decreasing concentration. Right? Let's rather say increase in concentration there. It will work against an increase in concentration by decreasing concentration. So, how the system increases concentration again is that concentration increases if the rate of the reaction that forms it increases. So, you remember that this means the forward and reverse reaction take place at the same rate. This means the forward reaction happens faster than the reverse reaction. So this would mean that C and D is now formed faster than A and B is formed. So therefore, this concentration will increase and this concentration will decrease. So what the system will do is, if the change that happens to the system is that we have an increase in the concentration of B, that's the change, the system will react by decreasing the concentration. And it will decrease the concentration by biasing the forward reaction. That's the only thing the system can do. It can bias a forward reaction or it can bias a reverse reaction. Okay. And biasing forward and reverse reactions make more of the one and less of the other. More, in this case, more product, less reactant. Okay. Now let's look at how this works for pressure. So if we have, let's say we have balancing numbers 2 there and 5 there. Okay. Now in total, these balancing numbers here add up to 3. So we have 2 moles of A, 1 mole of B, which gives us 3 moles of substance on this side. That is formed by the reverse reaction. Over on this side, we have 1 plus 5, so we have 6 moles of substance formed by the forward reaction. So now, if we increase pressure, that's the change that happens. The system will react in such a way to decrease pressure. So the way that it can decrease pressure is it can make fewer molecules, because fewer particles will collide less, will have a lower pressure. So if the change is that we want to increase pressure, or pressure is increased, that's the change, the system will react by decreasing pressure. And it's going to decrease pressure by making less moles of substances. So you can see in this reaction, forward makes 6 moles, reverse reaction makes 3 moles. So in this case, to decrease the pressure again, it's going to bias the reverse reaction, so that we have less moles of substances that can collide with each other, so the pressure is lower. Okay, so we're going to bias the reverse reaction. I hope that makes sense in terms of pressure. Volume is going to be opposite. Volume is inversely proportional to pressure. So if the volume is increased, the pressure is decreased. And if the pressure is decreased, then it's going to react by increasing the moles, because if you have more moles, you're going to have more collisions, which increases pressure. So for volume, if the volume increases, that implies a decrease in pressure. The system will try to increase the pressure by making more moles, because more moles of particles will collide more, which is equal to a higher pressure. All right? So that's what the system does with volume change. This is what the system does with pressure change and with concentration change. Okay. Then, what works a bit different, or that you just need to reason about differently, is if you have a change in temperature. So for change in temperature, you need to know that in the first place, before I even go here, you need to just remember that a Kc value, you know now how to calculate Kc values, change only with change in temperature. So if you had one Kc value and the temperature changed, then the Kc value is going to change. But if you had a certain Kc value and pressure, volume, or concentration changed and a new equilibrium is formed, the new equilibrium will still have the same Kc value. So Kc values change only with change in temperature for a certain reaction. Okay, that you just need to remember. Then, how it changes, what it does. You need to now remember that in grade 11, you did exothermic and endothermic reactions. So if this is your graph, this means this is the amount of energy the reactants have. We have a activation energy, and then the amount of energy that the products have. If the products have a lower energy than the reactants, it's an exothermic reaction, and the delta H, the enthalpy value, is negative. So it means that minus that gives us a negative answer. Okay, the energy of the products minus the energy of the reactants is negative. Now, this is an endothermic reaction, which means this is the energy, the heat energy of the reactants. After reaction, the heat energy of the products is higher. So it absorbed heat energy. It's endothermic, and the energy of the products minus the energy of the reactants will be positive. You can see that change is positive. This change is negative. Okay, now you need to remember an exothermic reaction increases temperature, and an endothermic reaction decreases temperature. So now, if the change that happens according to the Le Chatelier principle, if the change that happens to a certain equilibrium is an increase in temperature, the system will react to decrease the temperature. How does it decrease temperature? It biases an endothermic reaction. So it biases the endothermic reaction. Endothermic reactions decrease temperature again. Opposite is also true. If the change that happens to the equilibrium reaction is that the temperature is decreased, the system will react by increasing the temperature. What does it do to increase temperature? It biases the exothermic reaction, because exothermic makes it warmer again. Right. So it will be indicated which reaction is endo or exothermic by, they will give you a reaction like this. That will just be equilibrium. And then in brackets, they will write delta H is positive or delta H is negative. Whatever they write in that bracket there always counts for the forward reaction. So if they say in brackets delta H is positive, it means the forward reaction is endothermic. If they write in brackets delta H is negative, it means the forward reaction is exothermic. Okay. So now, please look at the examples on page 260 to just make sure you understand how the system will react in any one of these changes. Okay, so make sure you understand that first before you go on. Don't do the exercise yet, just look at the examples and make sure you understand the examples. Okay, now that you understand how the system will react with each change, now you need to understand how the graphs work for this, the Chatelier graphs. So if they give you concentration here on this axis and time here, then you can obviously see this is a product and these are two reactants, right? In a forward reaction, because there's zero product initially. Products increase, reactants decrease until they start being the same, and when they stay the same, it means that equilibrium has been reached. So that's the point of first equilibrium at that time. Right. Now equilibrium goes on, and then there's a sudden change. Now you will see here that in all of these, there's only one, what we call a spike, and that spike is what the change was, okay, in this case. So yeah, we can see that there was a sudden increase in, let's call that A, and this one B and that one C. So if we write a reaction of that, we can see that A plus B forms C, okay. Now, this means there was a sudden increase in the concentration of A. That's the change. Now the system reacts to that change by decreasing A. How will it decrease A? It biases the forward reaction, because the forward reaction uses A to form C. It decreases A. Now, if the forward reaction is biased, more of C will be formed. Do you see here? More of C is formed. But B is also used with A to form C, so B will decrease as A is increasing. Okay? So the spike indicates the change, and the gradual changes afterward indicate the reaction of the system. Okay, now there's another video also posted on Google Classroom that explains all the possible differences, all the possible things that could change. Yeah, so I want you to please, when you are done with this video, watch this video first before you do exercise 17 and 18. Right. When you are done with exercise 17 and 18, then there's a part of this chapter about the Haber process and the Ostwald process and how all of these things are used in those industries. You did the industries last week, so you'll understand what's going on there. So after working through those examples, please study those examples, and then you do exercise 19.